The Medusa Starship Drive offers us the chance to sail between the stars, propelled by nuclear bombs. The amount of energy released from a kilogram of an atomic bomb dwarfs what an equal amount of chemical fuel would release by a factor of around 1,000,000, and fusion bombs even more so. Thus, it's no surprise we have contemplated nuclear energy methods for running spaceships. But sometimes it can surprise folks that we've considered running those ships on actual atom bombs, rather than, say, a nuclear reactor and an ion drive. Nonetheless, the nature of high-powered propulsion is that it tends to be decidedly explosive, and you would be safer standing near several hundred pounds of explosives going off at once than next to your typical rocket flame. The other problem is that a nuclear reactor is a heavy thing compared to a bomb, and converts its energy into boiling water to turn a turbine and produce electricity, and then runs some form of electric propulsion like an ion drive, and tends to lose a lot of that compactness and low mass advantage that setting off a bomb has. What's more, while we have fission bombs and fission reactors, we don't have fusion reactors, just the bombs, and fusion is more compact than fission. For this reason, we have spaceship designs that seek to run on nukes. The best known is the Orion Drive, which uses an immense pusher plate on a spring behind a ship to absorb repeated blasts and translate them into a steadier thrust for the ship, allowing relatively fast interplanetary travel and indeed even interstellar speeds of a few percent of light speed. But this is not the only design, and today we'll be looking at another, the Medusa Drive. This one is principally different on the surface as it uses an immense parachute in front of the ship, rather than a plate from behind, to absorb the blast with the sail and drag the ship forward by tethers connecting them. This has many potential advantages over the classic Orion Drive, which we'll look at today, but I figure we should start by answering the first two questions that usually come up with this method, which is, first, why isn't the sail being torn to smithereens by the repeated blasts? And second, why aren't those tethers being shredded that are connecting the chute or sail to the ship? Ironically, the latter tends to be the one folks bring up most, and it is actually the easier part. I think folks are assuming the tethers run through the blast zone and are fragile, but they aren't coming much closer to the blast than the sail is, as they detach to its outer edge, and they would be thicker than the sail. In practice, I think you would place the sail much further from the ship than the blasts were from it, and have a long tether, since this minimizes how much forward shielding your ship needs, and it already needs a fair amount anyway to handle radiation and collisions at high speed. I always view it as a parachute in reverse, where it drags you forward rather than slowing you backward or down. In some ways though, it's a bit more like a jellyfish, and indeed that's how John Dale Solom's 1991 Los Alamos report had it, where he wrote, "One can visualize the motion of this spacecraft by comparing it to a jellyfish. The repeated explosions will cause the canopy to pulsate, ripple, and throb. The tethers will be stretching and relaxing. The concept needed a name. Its dynamics suggested Medusa." So a space jellyfish plus the snake-headed monster lady Perseus fought in Greek mythology. And that's the origin for the name for those who were wondering. Interestingly, I didn't know till I started outlining the script, even though it's mentioned in the article I first heard of it from, a 2012 write-up on it from Paul Gilster at Centauri Dreams, which if I haven't plugged recently, remains one of the best places to find out what's new and groundbreaking in deep space exploration, besides here of course, and also, of course, don't forget to hit the like and subscribe buttons. Another surprising thing I'd forgotten about that was in the article was that the basic idea probably goes to Freeman Dyson, who is probably the most referenced scientist on this channel and something of a personal icon to me. I say probably because he is listed as the author of a 1958 memo called The Bolo and the Squid that is still classified, and Dyson was heavily involved in the early Project Orion work, part of which involved trying to get around that giant pusher plate, which included options like reeling out cables with plates on the end of them which could absorb that momentum instead. An elastic tether is a good way to distribute a blast too, stretching it out and letting it drag your ship forward, as opposed to the big pusher plate and spring approach. That notion is also what I tend to have in mind when I suggest using a packed up solar or laser sail as your pusher plate. That's one alternative use of the big sail too, as a solar sail or laser sail. Your size is dictated by how big of blast you're using and how sturdy your sail is to that type of radiation, which by default is plasma and gamma rays and X-rays. Those cannot be reflected, at least not by current technology, so your sail is entirely absorptive. When it comes to momentum transfer, when two objects collide, be it two cars or a ball bouncing off a wall, or a photon hitting a giant sail, the most momentum that can be transferred is twice what the incoming object has, because it can bounce backwards at the speed it came in at, thus losing that forward momentum and gaining the same amount backward, which means whenever it hit, by conservation momentum, just gained double that momentum itself, and in the other direction. If it can't bounce or reflect, just get absorbed, like a gamma ray or high energy particle, then the most it can impart is the momentum it has when it strikes and merges into the object it hit. And it can do less too, much like shooting a piece of paper with a bullet. If the impact is too powerful for that absorbing object, it will just get punched through with only some of the momentum absorbed. So your sail can't be too fragile, and indeed you want it thin enough to be low mass and just barely able to handle the blast. You can recycle and repair bits of it during the journey too. Indeed, it will probably also be taking some damage from the front, as collisions with it will occur, and fairly often, as it's a lot wider than your spaceship probably is, in terms of collision cross-section. Of course, a big O'Neill cylinder-sized colony arc ship might only have a sail no wider than it is and just detonate thousands of nukes a day. But a shield in front of you is not necessarily a bad thing either, as an impact on that sail likely won't damage it much, but is likely to cause fragmentation to whatever it was hit by. There's also going to be some continuous pressure back on that sail, which you might spin along its central axis to keep it spread out, but you could also give shoves with the ship laser to keep forward of the ship if it drifted back or off to a side. You could send replacement sails this way or patches too. So that's the two big advantages it has over the Orion drive already, with Medusa, that the forward sail can be a light sail to gain extra free speed, and can act as a collision shield. Now, potentially you can pack a bomb around with material that will absorb all that gamma and superheat and release photons redshifted to some wavelength we can bounce. The question is if you could do that with less extra material than simply including another bomb would. But in an ultimate sense, if you get a way to bounce gamma rays, then your maximum speed for an identical ship goes up by the square root of 2, or 41.4% higher. So what's the actual process and pieces? Well, first, the sail or chute, as I've been calling it, more formally is known as a spinnaker, and it's a bit of an obscure sailing term for a sail designed to capture wind when sailing downwind. The spinnaker's curved shape allows it to fill with wind, providing significant propulsion by maximizing surface area exposed to the wind. This sail is used primarily for high-speed sailing when the boat is moving in the same direction as the wind, and it requires careful handling to maintain balance and to avoid collapsing or tangling. The same analogy applies to our Medusa sail, as we want to maximize the surface area exposed to the blast, which is also spherical, at least in its own inertial reference frame, so a sail shaped like a spherical cap works best. The name is mysterious and probably irrelevant. The best guess I've found is that the first ship that used the sail design in the 19th century was called the Sphinx, and it got mispronounced. A hemispherical blast sail is probably even more accurate, but I think an actual Medusa sail would be set up to change its geometry, by tightening or loosening the tethers holding it to the ship, or the main tether back to the ship they probably join into. Also by rotating the sail, or having cables in it that you could tighten, or that ran from the outer rim to the center, or you could alter the sail between flat disc and even a cone. And you might do that if you were blowing a lot of plasma on your detonations, for the same reason we do with rocket nozzle designs, or to pull power out for the ship by absorbing energy moving more or less perpendicular to the direction of motion, which can provide no thrust for you, but you could use that to generate electricity for life support and ship operations. So too, you might twist the sail or uncover one side to provide a shove-off axis, left, right, up, down to turn the ship. I find it easier to think of the Medusa as a version of a parachute or an umbrella carrying you into the wind, Mary Poppins style, but whatever works for you. And that analogy has resulted in me picturing Mary Poppins as having snakes for her hair, so maybe not the best visualization. I think the parachute works better for me because I tend to assume you are using it to slow down at a destination, and it would be shoved up by a laser sail to leave, so it is a parachute slowing you down in that case. So too, rather than have to carry all your fuel, thousands of nukes, someone could be firing them off from a cannon to go off in front of you, potentially even from relay stations out in deep space. Conceptually anyway, more likely they'd resupply by having a device that had an overrun speed on you that you could harpoon with a magnet on a tether and drag over to your ship for detonation at your own time of choosing, or even firing over the raw materials for making nukes. But you might prefer the trajectory and detonation of a nuke to be solely under your control, not that of whoever was running that ship. That way, if they went crazy, they not only don't have a huge nuclear arsenal at their disposal while entering your space, but you already have nukes targeted their way you can nudge onto a lethal course. Only ships entering an uninhabited system need to have their own nukes on board, and you could wait to give them their slowdown nukes till they were in deep space and moving at high speed away from your system. Now, we often imagine the tether only being a few kilometers long. We tend to assume we are using small nukes, and that as the sail absorbs them, again as a hemisphere or smaller spherical cap, that blast goes off in what would be the center of the sphere if that sail were a complete sphere. So every bit of the sail is getting the same shove, and this then pushes it forward and puts those tethers under tension, which results in the ship being pulled forward and the sail yanked backwards, but a net shift forward for both, while the debris of the bomb is moving backwards, or the reflected particle bouncing out the sail also gets that net momentum backwards, same as most propulsion systems. Overall momentum is conserved as much forward as back, and the propellant carries that backward momentum away. The suggested bomb was a 25-ton nuke, not 25 kilotons or megatons, just 25 tons that massed 25 kilograms itself. This is why you will see specific impulse listed for it as low as a few thousand seconds, which is still 10 times better than chemical fuels, of course. But it's simply a very low-powered bomb with a low yield-to-mass ratio. Bigger bombs with more yield per mass of bomb do much better, and you'll see it cited as high as 100,000 seconds of specific impulse. I think you could do better by using a very large design and high-yield fusion bombs. Probably not a shocking viewpoint from someone whose unofficial channel motto is that if brute force isn't working, you're not using enough of it. And of course, I'd also couple it with pushing beams to get underway. As a reminder, specific impulse is essentially the time an engine could hover in place on Earth. Earth's surface gravity of 1g times that impulse will get you the effective exhaust velocity too. And for 100,000 seconds of specific impulse, you're getting a speed of 490 to 980 kilometers per second. The lower value is if you want to slow down at your destination, which a flyby probe of course would not. That's a huge speed, but it's only a sixth or a third of 1% of light speed. Solem designed it in the 1990s before graphene was on the radar, so his basic design calls for high-strength polyethylene for the canopy of the sail, itself 500 meters in radius, or a kilometer across, or about 3,300 feet across, and something like 10,000 individual tethers. He also considered quarter-mil mylar as the canopy. I should note that while interstellar applications are always brought up with the Orion and Medusa drives, most of the analysis is done around them being interplanetary ships, so something using little 25-ton bombs weighing 25 kilograms, or 1 ton yield to kilogram, getting you 10 times the specific impulse a chemical rocket would, is very nice. That munition, incidentally, is basically the Davy Crockett or W-54 nuclear warhead that was designed for frontline use by infantry. You can do at least 40 times better than that, which translates to 40 times higher specific impulse, or 40 times higher speed. Needless to say, this would also work with more sophisticated bombs, like antimatter catalyzed fusion, which would also be more compact and probably ideal. Antimatter by itself would do even better, but there's easier ways to harness that as a rocket fuel. But if you are planning to tow an O'Neill cylinder to another solar system, I think you can justify using even nukes in the 10 megaton region as your fuel and propellant. That means a much bigger sail, or a stronger one, probably both, but graphene might be ideal for that role. That also lets you contemplate tethers hundreds of kilometers long, maybe even longer. You might wonder why, and in this case it brings up a third advantage the Medusa has over an Orion, in that the explosion can not only be further from the ship, but also further from whatever the ship is leaving. A ship in orbit of Earth that starts blowing nukes off to leave is likely to find itself shot down. But if it had a 1,000-kilometer long tether between it and the Medusa sail, it could be detonating nukes way up there instead, and smaller ones in particular would be rather harmless that far up. I think you'd unfurl that and have a beam pushing system shove you out past cislunar space. It saves fuel, and also means you could pass them off their packet of nukes only as they left cislunar space. You'd also be using that sail as a parachute against solar wind and sunlight as you enter your destination system, or dragging the ISM, interstellar medium, as you approach, both of which are more effective the faster you are going. So you use a laser sail to help you get to speed, and you use the parachute approach on the ISM to slow you from highest speed, and the nukes to finish slowing from higher speeds, and then solar sails for helping you as you get slower and enter the brighter regions of a star system, possibly deploying some smaller solar-powered beaming system at this point just ahead of you to further help you slow or to help slow other ships following in your wake. Why send a big colony ship when a colony fleet might work better? As with many of our spaceship designs, it tends to do best when used in tandem with other systems, though as always there's a cost to trying to employ and maintain multiple drive systems. This would tend to use the same material, same repair crews, and same onboard manufacturing and recycling, so it works well together. It's awesome because it allows interstellar travel without any new technology, much like the Orion, as opposed to options like gravitic propulsion that we'll discuss later this month on December 15th. But I thought we'd finish up today by talking about its interplanetary version, and for use out beyond the inner system, where sunlight is getting a bit thin to use for power or propulsion, and keeping a tight beam on a ship generated from the inner system might be impractical. Needless to say, if you're trying to leave an asteroid base or a comet, you can't be sending off a nuke right next to it, so you either need traditional thrusters, which are very wasteful, or some sort of launch assist from them, which requires significant infrastructure on their end. Or you can employ the Medusa to detonate the bomb a ways away and yank you clear. So we use the Solom 1990s design specifically, being mindful it could be upgraded in many ways. Those 25-ton bombs don't need to be very far off to be safe. That is a huge explosion, but we have conventional explosives of that scale, like the Moab, 11 tons, or the bigger Russian Foab, 44 tons, respectively short for the mother and father of all bombs, and both still 1,000 times weaker than those nukes used at the end of World War II. Still big, but not doing damage miles away. It might seem surprising that the design calls for a tether almost 5 miles or 8 kilometers long, especially when the spinnaker is just a kilometer wide, but that's less about protecting the ship than giving the tethers a lot of stretch. You are essentially storing the blast energy into them. They could stretch quickly and relax more slowly, distributing the pull, and in this case a tether that long for a blast that big would keep your pull to about 1 G. And of course it's tethers, plural, and a lot of them too. They are about a millimeter wide mylar tethers. One amusing limitation on tethers, and why it's handy to have many skinny ones, is they will warm up from stretching and relaxing, and that heat has to radiate away. 1,000,000 tethers with the same cross-section as a single big one 1,000 times wider will have 1,000 times more surface area to radiate with. In this version, you will be detonating bombs rather quickly too, on an order of about 20 to 25 a minute. You are practically machine gunning them out, and that makes a Medusa ship a pretty terrifying target if one pulls up to your planet to engage in trade and a dispute arises, though presumably you have far more weapons on your own orbital defense platforms. Obviously you can go slower with your detonation rate, but there's no advantage to detonating your bombs at a slower rate than your ship can handle. Mass of the tethers, bombs, and canopy probably are around half or more of your ship for the same reasons they always are under the tyranny of the rocket equation: more fuel and engine, higher speed. But you could go quite small in your drive and fuel mass with one of these and still pull off respectable speeds. The core design is something that could get you to Mars in, say, a month. In the basic design, it assumes 10 tons of canopy and 50 tons of space capsule for the crew and cargo. It all depends on your fuel ratio and how energetic that is per mass of fuel. As a loose calculation, it would generally exceed whatever an Orion drive can do, as the Orion drive's flat plate does not absorb as large a percentage of the blast as the hemispherical Medusa, and you'll see Orion drive estimates as high as 5% of light speed. Higher than that too, but on more dubious footing. And the Medusa would beat that out as its sail weighs less and it uses more of whatever bomb you're using for the Orion. Now, as noted, you can build much higher yield to mass ratio bombs than what I'll just nickname the Davy Crockett Medusa, and this was hardly lost on the developers of the idea. The concern is if your tethers can handle a bigger bomb stretching them. And again, we didn't have graphene or nanotubes when this was proposed, and from a practical perspective, we still do not. But another workaround was proposed, the servo winch, to get around the bungee jumping aspect of the tethers that stretches them out and could get impractically long for even hyper-strong materials. An appealing alternative is to use a winch system. Upon detonation, a motor generator-powered winch would release the line to the spinnaker at a pre-programmed rate, ensuring constant acceleration for the space capsule. During this phase, the motor generator generates electrical power, which can be efficiently stored. Once the capsule reaches the spinnaker speed, the winch would then reel in the line at a controlled rate, again maintaining constant acceleration. This retraction phase would produce less acceleration than the release phase, resulting in a net gain of electrical energy. Conceptually, you can think of this as throwing out your sail on a fishing line, playing out as the bomb shoves it forward, and reeling yourself back in more slowly behind it. It also gives you a good way to convert some of that blast into a reasonably steady electric supply, though in no circumstances are you detonating bombs the entire trip, unless maybe you're a speedy yacht traveling between two moons of a planet. You'd run out of fuel and would do better to accelerate faster. A nuclear reactor RTG hardly seems a concern for a steady power supply when the ship is carrying a massive arsenal with it anyway. That's a good point to close on, because the idea of a ship powered by nukes obviously brings up misuse. I've no easy answer for that, just some solutions like keeping the fuel packages at secure sites in orbit of Earth that could toss them to the ship once it was leaving cislunar space by other means, or by launching nukes at ships entering inhabited systems rather than having them carry their own slowdown nukes. But we always need to be mindful of the reality of spaceships, and another common saying on this show is that there's no such thing as an unarmed spaceship. It takes nuclear power to get a ship to high speeds because it's all that's energetic enough, and that ship, even if it's pushed up to speed by sunlight or some magic wormhole drive with no onboard fuel, still has a terrifying amount of energy. Moving at 1% of light speed, it not only could ram someone, but it could simply shoot a 2-kilogram slug off at something to ram it instead, striking with 9 trillion joules of energy, just over 2 kilotons of damage. And so 7 of those would strike an object with the power of the little boy atomic bomb used in 1945. No special weapon needed, they could have chucked a handful of garbage out their airlock. This does not mean nukes are safe, just any spaceship traveling at these kinds of speeds is incredibly dangerous. For my part, I think that it means embracing nuclear propulsion, as it simply does so much better than methods currently employed, but your mileage may vary. We talked about more nuclear systems in detail in our episode, The Nuclear Option, and of course more advanced spaceship drives, from the mundane to the highly theoretical, in our Advanced Spaceship Drive Compendium. And as mentioned, we'll be deep diving gravitic propulsion concepts in a couple weeks. But for now, let me know what you think of the Medusa Drive and its cousins. Leave a comment in the episode description below, or join in the chat on any of our forums on Facebook, Reddit, or Discord. And don't forget to hit those like and subscribe buttons. We've been talking about advanced spaceship drives today, and a lot of our audience would like to work on projects like this or other areas of the space industry or technology in general to really make an impact on this world or even other ones. But have you ever thought about how much of your life you spend at work? On average, you have 80,000 hours in your career. That's 40 hours a week, 50 weeks a year, for 40 years. It's a staggering amount of time, and your biggest opportunity to make a positive impact on the world, and worth investing some research time into finding out what's best for you. But where to start? That's where 80,000 Hours, a non-profit, comes in. They've spent over a decade conducting research, partnering with academics at Oxford University to figure out how you can have a fulfilling career while tackling some of the world's most pressing problems. No empty platitudes about following your passion, just hard data and evidence to help you find an impactful career. And here's the best part. All their resources are completely free. Whether you're just starting your career, thinking about switching paths, or wanting to make a bigger difference where you are now, 80,000 Hours can help. They offer tools like a free in-depth career guide to help you create a personalized plan, a job board with hundreds of high-impact roles, a podcast featuring deep conversations with experts about solving global challenges, even an episode on solving the Fermi paradox. If you join the newsletter now, you'll get a free copy of their in-depth research-led career guide sent to your inbox. Just sign up at 80,000hours.org/IsaacArthur. Stop settling for generic career advice. To get started planning a career that works on one of the world's most pressing problems, sign up now at 80,000hours.org/IsaacArthur. So we talked about interstellar spaceships able to take us to new worlds today, and next week we'll ask how technology might permit more off-the-grid living in the future, like allowing remote settlements on new worlds, or habitats in the spaceships that carry us there. After that, we'll explore another far more theoretical spaceship design as we see what science has to say about gravitic spaceship propulsion. Then we'll return to something a little more grounded in the here and now as we look at giant space elevator tethers attached to the ground and the improvements and updates that might allow us to build those in the next couple of decades. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or at Patreon, or check out other ways to help at isaacarthur.net. Until next time, thanks for watching, and have a great week.